see here. Let's go over what we're going to do today. Okay. So off my website here, under today's link, we're going to go over test review 3, and a lot of this worksheet is going to be with the 2 big topics we're going to see tomorrow, the extended topics, extended problems, which is the first derivative and second derivative, sine line, gathering, relative extrema, and point of inflection. And then the other one is particle motion. So we'll focus our attention today on those 2. Review worksheet 2, this has the other examples of the standalone problems, topics 3 through 7. And I'll get a chance to kind of go over the big picture of each problem today. And one of the curve sketching problems that we're doing today doesn't involve natural log, but I think the one with natural log is a good example problem for you guys to practice. We did this on Friday, but I put this link here in the hopes that you guys will have, if you have time today, to practice through. This is the key, but if you can go through the process and just have that, be able to practice that through, I think that'll be good. Okay. On this, if you look through Friday, Monday, and Tuesday, I think there are some good links for you guys to have as possible. Ones you want to maybe print out or have available in front of you as you're taking the test. One is the derivative here. So I haven't used all the rules here, but this is kind of organized in a way where if you look at from 1 to 15, these are the rules that we've been, 1 through 12, these are the rules that we've been using. Going back here, summary notes, I think these are the quarter sheets I've been kind of referring to, referencing as we go through each problem. I think this is also good if you want to have this in front of you. Okay, steps for different processes are here. Common mistakes, I'm going to go over this sheet as well. Okay, so let's go to worksheet 3. Okay, so worksheet 3. We have a function defined by x cubed over e to the x. We're going to find a well, I'm not going to ask for you to find a domain on the test, but I think it's good to look for the domain. It kind of helps us understand how our sine line, what our restrictions are going to be for our sine line. A place is in the denominator, right? Whatever makes the denominator 0 is going to be where our potential issue is. So if you set e to the x equal to 0, you're going to see that there's e to the x is never equal to 0. And so we have no restrictions at all. There's no natural log. There's no restriction with negative numbers. There's nothing that makes the denominator 0. Our domain is all real numbers. don't have to worry about range. And now part C, we're going to find relative max, relative min using first derivative test. So we need to find the derivative. To find the derivative, what do we have to involve here? Quotient rule. Okay, so try that. Go through quotient rule, and we'll compare our answers. Okay. Now, once you find the derivative, we're going to look at the numerator to see what you can do to clean up, combine like terms, factor out GCF. We're going to work our way down to our simplified form so that we have an easier time looking for critical points. F prime g minus fg prime all over g squared. Once I'm here, I see some common factors I can take out. E to the x is shared, x squared is shared. I can take out one of the e to the x's between my numerator and denominator. So here we have our cleaned up f prime boxed off in red. Okay, what's next? Good. Points, numerator and denominator equal to 0. Doesn't mean that we're always going to find critical points that will amount to anything, but we always want to make sure we look. Okay, so set the top equal to 0, set the bottom equal to 0. All right, numerator is straightforward. The denominator, though, e to the x equal to 0. Okay. All right, so let's try to solve for this. E to the x equal to 0. If I try to get that x to come down, I have to involve natural log, right? Natural log will help me get that x to come down. So when I do that, though, I'm going to end up with natural log of e to the x equals natural log of 0. The x comes down. That's fine. But what do you notice on the right side? Natural log of 0. It's undefined, right? You can plug in the calculator and see that it will give you undefined. Or you can think about the graph. Natural log graph has an asymptote at 0, so natural log of 0 doesn't exist. So we looked, no critical point there, but we still have 2, right? We still have 0 and 3 from the sign line. F prime sign line, we put 0 and 3. We're going to test. The nice thing, well, we know the domain is all real numbers, so we're going to test negative number to the left of 0. So 0 is not a starting point. We're going to do negative left of 0, between 0 and 3, and to the right of 4. So if I put negative 1 into my derivative, negative 1 squared is positive, e to negative 1 is positive. So the x squared and e to the x are always going to give me positive values. I'm not going to have any issues with negative. So that tells us that it's really the 3 minus x. 3 minus x is really driving the information about the sign of my slope. So if I put negative 3 in for x, I get 3 minus negative 1. That's positive. Everything else is positive. If I put 1 in for x, 3 minus 1 is positive. Still, everything is positive, so positive slope. But if I put 4 in, I get 3 minus 4, I get negative. The rest is positive, so there's my sign line. I can, everything I need, most everything I need is from that sign line. Relative extrema, there's only one, right? X equals 3, right? And it's a relative what? Relative maximum. And then if I ask you for the order pair, you would plug 3 back into the original. I'm not going to ask you to graph it, so just give me that y value. And then if I ask you for justification, you would say because f prime changes from positive to negative. Okay. (27 over e cubed is the y value. Now, moving on to our second derivative sign line. We want to find the second derivative. So look at f prime. We're going to use what again? Quotient rule. What I would do is I would clean up the numerator a bit. Otherwise, you got to do a product rule within the quotient rule. So I would get the parentheses to, the parentheses were good for us to find critical points, but before I move on to the second derivative, I'm going to resolve that parentheses so that when I do f prime, I want to deal with another set of parentheses within my numerator. So there's my cleaned up f prime in terms of without the parentheses up top. And now quotient rule. Now, once you find the derivative, you're going to have to do a little bit of cleanup with the numerator. Take out GCF, combine like terms, right? Again, we should be able to get it to the point where we can look for critical points. You can definitely distribute and combine some like terms, but I looked at this and I said, well, I'm just going to go ahead and pull an e to the x out between this expression and this expression. If I can just factor e to the x out quickly, it may not be the full GCF process. I want to rewrite e to the x so many times. But eventually, we do want to get to the point where we can get it cleaned up so that we have a good place to look for critical points. Okay, so I factored e to the x out. I'm left with that 6x minus 3x squared minus parentheses 3x squared minus x cubed. Combine those like terms, distribute the negative through. Okay, so just like before, we're looking for critical points, right? But now these critical points are going to be candidates, not for relative extrema, right, but for point of inflection. So we set both the numerator and denominator equal to 0. X equals 0, that's 1. E to x equals 0, that's the same issue as before, right? Nothing there. X squared minus 6x plus 6. Can we factor that? Okay, so it's a quadratic formula. I won't give you a quadratic formula on the test, but we'll just go through that process just so we can see how everything works together when we do find these critical points. Ends up being 6 plus root 12 over 2. I didn't reduce it, but we have 3 critical points, right? We have 1, 2 here, and we have 1 there. We're going to place those critical points onto a sign line, and I'm going to choose values in each interval to test against my second derivative function. And I just want to gather information about positives and negatives, right? Positive would tell us that the graph is concave up. Negative would tell us concave down. So we have 3 candidates for points of inflection, but now after the sign line, can we confirm that these are all points of inflection? Yes, yeah, change in sign, right? So after you find your critical points, you still have to make it go through the sign line, right? And if I ask you for order pair, you'll plug all these back into the original function, and your reasoning would be because f double prime changes signs. So on the test, it'll be either one or the other. Either I give you f and I ask you for relative max, relative min, or I give you f and I ask you for concavity point of inflection. Right. It's a little bit too long to put into the test, so it'll just be one or the other. But we want to be familiar with both parts, so whatever you see, you'll be ready for it. Okay. Any questions with relative extrema POI problems? Okay, let's turn to the back. Does anybody still need this? Okay, let's turn to the back and let's try number 3. This is a particle motion problem. Velocity, position 4/3 e to the 3t minus 8t. And you're asked to find velocity and you're asked to find acceleration.
Mr. Yang, I actually did miss something on the back page. Could you go back for like 1 second?
Yeah.
Okay, thank you.
Okay. So from position, we're going to find the velocity, and then from velocity, we're going to find acceleration. Is there any need for any additional rule besides e to the 3t and 8t? Do we have to make it go through any product rule? Okay, there's no product rule, right? Okay. What if a problem looked like this? Product rule, right? So sometimes if a product rule is there, I want you guys to be able to recognize it, right? You see parentheses, that's an indication that maybe there's product rule. If you have 2 things that are next to each other being multiplied and there's no way to merge them together, that's also product rule. Okay, not in this case. but to be able to recognize it sometimes is the hard part. Okay, so we find the derivative of position. Position will take us to velocity. So e to the u times u prime. And then we go through derivative process again to get from velocity to acceleration. Here's acceleration. Any questions there? Yeah. Why did I multiply 4/3? It's a coefficient, so coefficient is going to just tag along to the derivative. Right. So 4/3 stays. E to the u becomes e to the u times u prime. And then I got the 3's to cancel out.
Mr. Yang, isn't it 12e2t or is it?
Okay, so when we find the derivative for e to the u, it's just e to the u times u prime. It's not e to the u minus 1 times u prime.
Oh, okay, thank you.
Right, so we don't do power rule for this. Yeah. So if you look at the rule here, all right, the rule is it's not e to the u minus 1, right? It's the original function times the exponent's derivative. All right, good so far? All right, for part C, when is a particle at rest? How do we find that? Set velocity equal to 0. Okay, let's do that. So if I want to set velocity equal to 0, I'm going to solve for t. So I'm going to bring that 8 over, divide both sides by 4. And I'm down to e to the 3t equals 2. So how can I get to that 3t? Yeah, oh yeah, take natural log both sides. Yeah, so now natural log both sides. We can then take advantage of log properties. We can bring that exponent down. Exponent comes down, 3t. Natural log of e just goes away. And now we can have a lot easier time solving for t, divide both sides by 3. And then we have our location. We have the t value where object is motionless, right? Velocity is 0. Let me extend this a bit and ask you, when is a particle moving left? So if I ask you when the particle is moving left, what do we need to create so that we can?
So when velocity is negative?
Yes, but what should we have in place to make it easier for us to identify that velocity sign line? Okay, so we got to create a velocity sign line. Yeah. Okay. What can we put onto that sign line? Mm-hmm. Did we find it already? Yeah. Good. So particle moving left, it's almost like just finding f prime and seeing where f prime is negative, right? I mean, we know how to do it from a first derivative standpoint. It's the same thing, it's just that we named it differently. Instead of prime, we call it velocity. Instead of velocity 0, or instead of slope 0, we say velocity 0. And then instead of left, or instead of rising and falling, we're calling it negative, moving left or moving right. So it's the same process as your first derivative test. It's just we called it a different context. Okay, so we're going to test either side of our critical point. I know it may be strange for us to be dealing with time that's in the negatives, but if they don't, on the AP exam as well, if they don't give you a restriction, sometimes that means we're going to treat t for all real numbers. Okay, so unless they say specifically t is greater than 0, then we don't want to just restrict negative values unless the problem tells us to restrict it. So into the velocity function, e to the 0 is 1. 4 times 1 is 4. 4 minus 8 is negative, so negative velocity. And then to the right of my critical point, if I plug 1 in, e to the third power, that's what, 2.7 to the third power, that's around 8 or 9. 9 times 4 is 36. 6 minus 8, still positive. So we can say our particle is moving left in which interval? Zero is just a test number. Negative infinity to natural log 2/3, right? So we don't want to include the test values in our interval. They're just telling us whether it's positive or negative. After that, we ignore those numbers. We're just using critical number and infinity if we need it. Okay, so highlight that process. You're going to see that on the test. It wasn't included in this example, but we need to know how to do that. For D and E, it's just asking for velocity at 3 and acceleration at t equals 3. We just evaluate using our appropriate functions. Okay, moving on to F and G. It says that t equals 3 is the velocity of the particle increasing or decreasing. How do we determine increasing, decreasing velocity? Where do we look? Just acceleration, right? What about speed of the particle, increase, decrease? Compare signs, yeah. So velocity is increasing because acceleration is positive. Speed is increasing because both velocity and acceleration are the same sign. They're both positive. Okay, so you know what to expect for your particle motion problem, right? Okay, anybody still need this? Good. Okay. We did the two extended problems, relative max, relative min, concave up, concave down. Well, yeah, and I said before, right, it's either one or the other on the test. Particle motion, we did that, and then here are the other topics, the standalone problems. You're going to see one where you're going to have to find the derivative of a log term. Maybe you need to do some expansion before you find the derivative. Maybe you have to involve base E or base A log and exponential rules, depending on what the problem says. It may involve product, quotient, or chain rule, depending on what the problem. Find tangent on the equation. Okay, so that's where we got to find the derivative, then use the x value to find the slope. From there, find order pair and slope, point slope form. Implicit differentiation. We need to be able to sometimes involve log expansion if it applies. Product quotient rule if it applies. Log differentiation and derivative inverse at a point. So all these examples are on that second worksheet that is under today's link. So I'm just going to kind of go through them and just kind of review the big picture here. So first up is a problem where we want to first rewrite in rational exponent form. So write this as parentheses raised to the x over 7. And if you look, this is not going to be chain rule. This is not going to be power rule. This is not exponential rule. This is a variable to a variable. We don't have a rule for this, right? So we have to find a way to present this in a different form. And the idea is, why don't we find a way to get that exponent to come down? So the way we do that is we introduce natural log to both sides, and we go through log differentiation. So once that 1/7 x comes down, we see product rule that can handle the derivative on the right side. Implicit that will handle derivative on the left side. Bring the y over to the right, and then replace the y back in terms of the original x. The derivative will be messy, but that's fine. Yeah, all this is on that link. I don't expect you guys to work all this out right now. I will work through these if you want me to on the help session, but I'm just going to go through the big picture here. Okay. We need to be able to find the derivative of inverse at a point. So this is where we have to understand that the number that's given to you is not the x value of the function, it's the y value of the function. So the first thing we do is we put that 2 in for the y value position. We solve for x, but it's not going to be factorable, so we're going to have to do a little bit of guess and check. But it should be an easy number to find. Any number between -2 and 2. So in this case, it ends up being 1. That number is going to be important later on because we're going to find the derivative of the function. And that's going to help us get to the slope. And if I find the slope is 5. That's going to get really allow us to use that number to get to our answer, because the slope of the function at a point is going to be the reciprocal of the slope of the inverse at its corresponding point. So we're just take the reciprocal of the slope. And to help you see a visual, if you have a function and its inverse, and once we identify their corresponding points, their slope, their steepness, at that point, we'll have that relationship. Whatever slope we find, the other point on the inverse side of things is going to have a slope that is also the same sign, but it will be the reciprocal, a lot less steep. Okay, so we need to understand that process there. Next up, if you see a log problem, consider the possibility of expanding. All right, so here I see one numerator term, I see two denominator terms. So basically, the way you expand is the numerator is going to be part of a positive log, and your denominator will be part of a negative negative log. Once you expand partially, then look for any further expansion, any exponents that can come down, and then you can treat each like a separate problem and apply the appropriate log rule to each term. Okay. And then implicit problem. Recognize the need for implicit, especially if you see multiple y's within the equation. What do we need to involve here? Quotient property, good, right? So expand, right? We don't want to do the derivative, at least not yet. Expand as far as you can, and there's also something else going on here when we get to the derivative. You got to use what? Recognize when you need product and quotient when you see it, okay? So we apply all the derivative process, bunch of dy dx's pop up, group them together, factor it out, and then solve for dy dx. Okay, one last thing I want to do is go over some common mistakes I've seen in the past, and especially derivative rules involving logs here. Okay, so here are a couple of ones I've seen. Okay, so here's one. If I asked you to find a derivative, what would you do first? Yeah, you would expand, right? You would expand, right? And then once you expand, then you do u prime over u, right? So that's the correct process. What I see some students do is this. They would take the natural log of both sides, and they would involve log differentiation. So we don't want to do that because then you're complicating the problem, right? We only do log differentiation if there are no logs in the problem. If there are no logs in the problem, then you can do log differentiation. But also, we only want to do log differentiation in two scenarios. One is where the right side of the equation is just too messy. You got product, quotient, chain all going on in one large fraction. You want to split it up. Or it's a variable to a variable where you're forced to have to go through log differentiation. But other than that, we don't want to introduce a log into another, so we don't want to create different layers of log problems. It just makes it too complicated. So we don't want to do that. Okay, I see this as well. If I asked you to find a derivative, are you able to do anything beforehand? We can't. Okay. This is not eligible for expansion, but I see it anyways, though. I see this. It seems like we can distribute, but we can't create our own property if it's not already listed. Right. Now, if these were multiplied together, then you can expand. But if it's addition or subtraction, we can't go any further. But if it looked like this, then yes, we can make this natural log of x squared. Okay. but we can't do this. Okay, y is equal to e to the 5x. We have a specific rule for base e, and the rule is e to the u times u prime. But I see some students trying to use power rule for this because that looks like a variable. So I see this. They bring down the 5x, they keep the e, and they subtract 1 from the exponent. So this is not power rule. Okay. We don't want to do this. I see this as well. If I ask you for the derivative, how would you start this process? Yeah, you would bring that down that 4, right? And then you would apply what?
Just find the derivative.
U prime over u, right? You would say negative 20x cubed. Okay, so that's the correct method. This is what I see. Students would think of this as chain rule. They would think of this as the same thing as if it was just 3 minus 5x to the 4th. And they would do this. They would bring down the 4, keep the natural log, subtract 1 from the exponent, and then multiply it by negative 15x to the 4th. Okay, so this is not the same thing. Can't do that. And then one more. So the rule for e to the u is e to the u times u prime. But I see the knob where sometimes students either mix it up or they get confused between this and natural log rule, and they end up merging them together. And I see this, y prime is equal to e to the u times u prime over u. So u prime over u is just for natural log. It's not for e to the u. So I see that getting confused there. So our derivative is just e to the u times u prime, not e to the u times u prime over u. Okay, so that's not correct. Yeah, so those are the big things that students struggle with, that I see with derivatives. Okay, so help session, 5th period, second half, 5th period, after school, 3:30, tomorrow morning, 7:15, on Teams as well as face-to-face. All those sessions have been recorded, even the ones that I've done the past few days, if you want to check those out. Reminder that tonight is the due date for your assignment if you want to do recovery for the Chapter 3 test. Okay, so that's due tonight. Teams, you're going to submit Teams. And then once I see that, you need to let me know whether you want to take it 7:15 on Friday morning or 3:30, or sorry, 4:30 Friday afternoon, because I need to assign the appropriate test to you. And then you'll log into the Teams help session page, and you'll open up your live feed just like on your on test days. Any questions? Yeah.
This is more just like a general question. I can see potentially time being maybe an issue depending on the test. What would you recommend to?
I think time. I think we've kind of taken a lot of the parts out of the test. There's no graphing, and you're only asked to find relative max, relative min, or POI. You're not going to do a whole extended problem. And maybe some of the longer problems don't have to worry about cleaning up. So once you find the derivative, you know, that's all you need to do. Yeah. And I'm looking for the process as well. So if you're stuck at the end, that's not as big of an issue, right? But being able to get through the beginning and middle of the problem, that's, you know, I want to see that process, right? So if you run out of time at the end of the problems, don't run out of time because you didn't get to start any problem at the beginning. Yeah. But yeah, so as soon as you guys come in the class tomorrow, I'll start handing out the test to give you guys any additional time that you need. Okay, bring your notes, bring your calculator tomorrow. If you have any questions, you can send me a message through Remind. Okay, otherwise, I'll see you tomorrow. Have a great day, guys.